Every night, the sky above our planet looks calm. But it isn't. Invisible storms passes through Earth every second. Rivers of energy emitted from the surface of the sun are crossing space at impossible speeds. Most of the time, we never see them. But sometimes, the sky breaks its silence. Light appears where darkness should be. It moves. It breathes. It watches back. We call it the aurora. But here is the problem. The same energy that creates these beautiful lights is strong enough to tear atmospheres away from planets, to shut down satellites, to collapse power grids, to reach into the systems our world depends on. So why doesn't it? Why does Earth glow instead of burn? For centuries, people believed the lights were messages from gods, warnings, spirits, signs of something watching from above. But science uncovered something far more unsettling. The aurora is not a decoration in the sky. It is a signal, a visible trace of a hidden battle between a star that never stops releasing energy and a planet struggling to control it. The lights appear near the poles for a reason. They move like living things for a reason, and they arrive more often when our technology begins to fail for a reason. If solar particles are hitting Earth hard enough to light up the sky, why hasn't our atmosphere already disappeared, the way Mars's did? What is Earth doing differently? And how close have we already come to a solar storm powerful enough to push that system past its limits? In this video, we will follow the path of that energy, from the core of the sun across the emptiness of space. By the end, the aurora will no longer feel peaceful, it will feel precise, because you'll understand something hidden in plain sight. The sky doesn't glow to entertain us. It glows to protect us. An aurora is a natural light display that forms high above Earth in the upper layers of our atmosphere. But this light does not come from fire, reflections, or clouds. It comes from energy arriving from space. What we are actually witnessing is something invisible becoming visible. Far above our heads, tiny charged particles, mainly electrons, are racing toward Earth at incredible speeds. These particles originate from the sun. When they reach our planet, they are guided by Earth's magnetic field toward the polar regions. As these particles slam into atoms of oxygen and nitrogen in the atmosphere, energy is transferred. Those atoms briefly become excited, unstable, and when they return to their normal state, they release that excess energy as light. That light is the aurora. So when we watch auroras dance across the sky, we are not seeing light that begins on Earth. We are seeing space touching our atmosphere. The name Aurora comes from Roman mythology. Aurora was the goddess of dawn. To ancient observers, these lights looked like a strange sunrise appearing in the night sky. When the display occurs in the northern hemisphere, we call it the aurora borealis, the northern dawn. In the southern hemisphere, it is called the aurora australis, the southern dawn. Scientifically, these two are identical. They happen at the same time on opposite sides of the planet, mirroring each other along Earth's magnetic field. We simply see the northern aurora more often because most of humanity lives in the north. Now, an important question arises. If the sun shines on all planets, why don't all planets have auroras? For auroras to exist, three conditions must be met. First, there must be a source of charged particles, like the solar wind from the sun. Second, the planet must have an atmosphere. And third, it must have a magnetic field strong enough to guide those particles. Earth has all three. That combination makes auroras possible. Without a magnetic field, charged particles would simply scatter. Without an atmosphere, there would be nothing to glow. And without the sun, there would be no energy to begin with. This is why auroras are rare in the universe, and special. But long before we understood any of this, humans were already deeply affected by auroras. Across cultures and across centuries, people looked up at these moving lights and felt something powerful. Auroras are silent. They are enormous. They appear without warning, and they move as if they are alive. The human brain is wired to search for intention. When something moves with purpose, we instinctively assume it means something. Ancient cultures did exactly that. To the Norse, auroras were reflections from the armor of fallen warriors or bridges to the realm of the gods. To Inuit cultures, they were spirits of ancestors playing games in the sky. In China, they were described as dragons of light twisting through the heavens. In medieval Europe, red auroras were often seen as warnings of war, famine, or plague. Different cultures, same reaction. No one believed auroras were random. Even when early scientists began studying the natural world, auroras remained deeply confusing. Some believed they were reflections of sunlight off polar ice. Others thought they were atmospheric fires, electrical storms, or strange vapors rising from the earth. But none of these theories could explain one critical fact. Auroras occur incredibly high above Earth, sometimes more than 500 kilometers up. That is far above clouds, weather, or any known atmospheric fire. Auroras were simply too high, too large, and too organized to be explained by Earth alone. In 1619, Galileo Galilei observed a red aurora over Europe. He named it Aurora Borealis and suggested it was caused by sunlight reflecting off vapors in the atmosphere. His explanation was incorrect, but his approach was revolutionary. Galileo treated auroras not as omens, but as natural phenomena. For the first time, auroras became a scientific problem rather than a supernatural message. The real breakthrough came centuries later, when scientists noticed something strange. Whenever auroras appeared, magnetic compasses behaved oddly. Needles drifted, measurements fluctuated, and during intense auroral events, early telegraph systems malfunctioned or even caught fire. Scientists like Anders Celsius and Alexander von Humboldt began connecting auroras to Earth's magnetic field. This was a turning point. Auroras were not just lights in the sky. They were linked to invisible forces surrounding the planet. By the 19th century, another connection became impossible to ignore: the sun. Strong auroras followed periods of intense solar activity. During the famous Carrington event of 1859, auroras were seen near the equator. Telegraph operators were shocked by electric currents traveling through their wires. The sun had reached across space and touched Earth. By the 20th century, with rockets, satellites, and space-based instruments, scientists finally confirmed the truth. Auroras are created by energetic particles from the sun, guided by Earth's magnetic field colliding with our atmosphere. They are not atmospheric events. They are not optical illusions. They are space physics made visible. And yet, even today, auroras still feel mysterious. New auroral forms like Steve have only recently been discovered. Fine details of particle acceleration are still being studied. Auroras remain one of the few natural phenomena where advanced physics and pure beauty exist in the same moment. To truly understand auroras, we must stop looking at Earth for a moment. We must lift our attention outward to the source of the energy itself. Everything we see glowing in the polar skies begins far away, inside the sun. The sun is not a calm object. It is not a steady lamp in the sky. It is a massive, restless engine of energy. At its core, temperatures reach millions of degrees. Under this extreme pressure and heat, hydrogen atoms are forced together, fusing into helium. This process, nuclear fusion, releases enormous amounts of energy. That energy slowly makes its way outward and eventually escapes into space as light, heat, and something far less visible, but far more important for auroras, charged particles. The sun is constantly releasing these particles in all directions. This continuous outflow is called the solar wind. The solar wind is not dramatic. It is always there. It flows outward like a cosmic breeze, carrying electrons and protons across the solar system. If the sun only produced this gentle wind, auroras would be faint and rare. But the sun does much more than that. The surface of the sun is tangled with powerful magnetic fields. These magnetic fields twist, stretch, and snap under extreme conditions. When that happens, energy is released violently. Dark regions called sunspots appear where magnetic fields are especially strong. These are not cooler spots by normal standards. They are still thousands of degrees hot, but they are cooler than the surrounding surface. Sunspots are signs of magnetic stress, and when that stress is released, the sun can produce solar flares, sudden bursts of electromagnetic energy that race outward at the speed of light. Even more powerful are coronal mass ejections, or CMEs. A CME is not just light, it is a massive cloud of magnetized plasma, billions of tons of charged particles blasted into space. When one of these clouds is aimed toward Earth, the journey begins. It takes anywhere from 15 hours to several days for solar material to travel the 150 million kilometers between the sun and our planet. And here is something critical to understand. Not every solar storm creates auroras. Earth is not defenseless. Most of the time, Earth's magnetic field deflects the solar wind around the planet like a shield. The particles flow past us, harmlessly redirected into space. Auroras only occur when solar activity is strong enough and aligned just right to disturb that magnetic shield. The sun also operates on a rhythm. Approximately every 11 years, solar activity rises and falls. During solar maximum, sunspots increase, solar storms become more frequent, and auroras appear more often and farther from the poles. During solar minimum, the sun is quieter, and auroras retreat toward higher latitudes. This cycle is one of the reasons auroras feel unpredictable to casual observers, yet follow long-term patterns for scientists. What makes the sun unique in aurora science is not just its power, but its reach. The sun does not merely shine on Earth, it touches Earth. Its magnetic storms stretch across space. Its particles interact with our magnetic field. Its activity directly influences what happens in our skies, our power grids, our satellites, and even our technology-dependent civilization. Auroras are one of the few natural phenomena where we can see this connection with our own eyes. When the sun becomes active, it sends energy outward. When that energy reaches Earth, our magnetic field responds. And when the response becomes intense enough, the sky lights up. So when we watch auroras ripple across the polar night, we are not watching something that began. The sky lights up. So when we watch auroras ripple across the polar night, we are not watching something that began above our heads. We are watching the after effects of a star that is 150 million kilometers away, reaching across space and shaking our planet's invisible defenses. In that sense, auroras are not local events. They are solar events, written across Earth's atmosphere. And now that we understand the sun's role, the next question becomes unavoidable. If the sun is constantly sending energy toward Earth, what exactly is Earth doing with it? To answer that, we must understand Earth's magnetic shield itself, the structure that decides whether solar energy is deflected or transformed into light. Now that we understand the sun as the source of auroral energy, we must return our focus back to Earth. Because even the most powerful solar storm cannot create auroras on its own. Something on Earth must receive that energy, shape it, and decide where it goes. That something is Earth's magnetic field. Deep beneath our feet, far below the crust we live on, Earth's core is in constant motion, a solid inner core surrounded by a swirling ocean of molten iron and nickel rotates and churns over geological time. This motion generates electricity, and moving electricity creates magnetism. Together, this process forms what scientists call the geodynamo, the engine that produces Earth's magnetic field. This magnetic field extends far beyond the surface of the planet. It is invisible, but incredibly powerful. It surrounds Earth in a vast protective bubble. That bubble is known as the magnetosphere. If we could see it, the magnetosphere would not look like a perfect sphere. On the side facing the sun, it is compressed by the solar wind, flattened like the front of a shield. On the night side, it stretches far into space, forming a long tail, the magnetotail, extending hundreds of thousands of kilometers. This shape matters. The magnetosphere's primary role is protection. It deflects most of the charged particles streaming from the sun, guiding them around the planet rather than allowing them to strike directly. Without this magnetic shield, Earth's atmosphere would slowly be stripped away, much like what happened to Mars. But this shield is not sealed. It has openings. Near the north and south poles, Earth's magnetic field lines dip downward and connect directly to the atmosphere. These regions act like funnels, guiding charged particles inward instead of deflecting them away. This is why auroras form near the poles. Solar particles that manage to enter the magnetosphere are trapped and guided along these magnetic field lines. They spiral downward, accelerating as they move toward the upper atmosphere. These pathways form glowing rings around each pole, called auroral ovals. The location of these ovals is not fixed. During calm solar conditions, they stay close to the poles. During strong solar storms, they expand outward, allowing auroras to appear at much lower latitudes. Within the magnetosphere, energy does not move smoothly. It is stored. On the night side of Earth, in the stretched magnetotail, solar energy accumulates like tension in a pulled rubber band. When that tension becomes too great, the magnetic field suddenly reconfigures. This release of stored energy is called a magnetospheric substorm. During a substorm, energy rushes toward Earth along magnetic field lines, accelerating particles downward. The result is sudden, dramatic auroral brightening. The sky seems to explode into motion. These moments are some of the most vivid auroras ever observed. But there is another layer to this system. Electric currents flow through the magnetosphere, connecting space directly to Earth's atmosphere. These currents, known as field-aligned currents or Birkeland currents, carry energy along magnetic field lines into the polar regions. In a very real sense, Earth and space are connected by invisible wires of electricity. Auroras form at altitudes between about 80 and 500 kilometers above the surface. This region lies between the dense lower atmosphere and the near vacuum of space, a boundary zone where both atmospheric chemistry and space physics collide. The color, brightness, and shape of auroras depend on the type of particles involved, their energy, the altitude at which collisions occur, and the strength of the magnetic disturbance. Without Earth's magnetic field, auroras would not exist as we know them. Solar particles would strike the atmosphere randomly. There would be no curtains, no arcs, no dancing lights, only faint, chaotic emissions, if any at all. Auroras are not simply caused by the sun. They are shaped by Earth. They are the visible signature of a planetary defense system responding to a star's energy. And now, with the sun supplying the particles and Earth guiding them, we arrive at the heart of the phenomenon itself. What exactly happens in the moment when a charged particle collides with an atom in our atmosphere? How does invisible motion become visible light? To answer that, we must move closer still, into the collision zone itself. We have followed the energy from the sun. We have watched it interact with Earth's magnetic shield. Now we arrive at the moment where something invisible becomes visible. This is where the aurora is actually created. High above Earth's surface, in the thin upper atmosphere, charged particles accelerated by the magnetosphere finally collide with atoms and molecules of gas. This region is called the ionosphere. It is neither fully atmosphere nor fully space. It is a boundary zone, a place where space physics and atmospheric chemistry meet. The main particles involved in auroras are electrons. They are small, fast, and easily accelerated by electric and magnetic fields. Guided along Earth's magnetic field lines, these electrons spiral downward at enormous speeds. When they reach the upper atmosphere, they collide with atoms of oxygen and nitrogen. These collisions are not destructive. They are energetic interactions. When an electron strikes an atom, it transfers energy to that atom. The atom absorbs this energy, and one of its electrons is pushed into a higher energy state. This state is unstable. Atoms do not like to stay excited. Within fractions of a second, the excited atom returns to its normal state. When it does, it releases the excess energy as a photon, a particle of light. That photon is what we see as an aurora. So an aurora is not a continuous glow. It is made of billions of microscopic flashes of light happening simultaneously across the sky. The color of that light depends on three main factors: the type of gas involved, the energy of the collision, and the altitude at which it occurs. Oxygen is responsible for the most common aurora color, green. Green auroras form when oxygen atoms are excited at altitudes of about 100 to 150 kilometers. This emission is strong and efficient, which is why green is the color most often seen. At higher altitudes, above 200 kilometers, oxygen can produce red auroras. These are fainter and slower to form, which is why they appear during strong solar storms and often look diffuse. Nitrogen produces different colors. Molecular nitrogen and ionized nitrogen emit blue, purple, and pink hues. These colors typically appear at lower altitudes, where the atmosphere is denser and collisions happen more frequently. When multiple gases emit light at the same time, the colors mix. This creates the complex palettes we see in bright auroral displays. But auroras are not just about color. They are about motion. Auroras form shapes because the incoming particles are guided along magnetic field lines. These field lines are not straight. They curve, twist, and ripple. As streams of electrons follow these paths, they create the familiar auroral curtains, long vertical sheets of light that appear to hang from the sky. Thin beams of light, called rays, form when particles are tightly focused. Broader arcs form when the particle flow is more spread out. Sometimes the aurora appears to pulse, turning on and off rhythmically. These pulsating auroras are caused by interactions between particles and plasma waves within the magnetosphere. In rare cases, when the aurora forms directly overhead, it can appear as a radiant burst with rays spreading outward in all directions. This is known as an auroral corona. The speed of auroral motion can be deceptive. Although the lights appear to drift slowly, the particles themselves are moving at incredible velocities. What we see is the changing location of collisions, not the movement of light itself. Auroras also vary in brightness. Some displays are faint, barely visible to the human eye. Others are so bright they cast shadows on the ground. This brightness depends on how much energy is being delivered from space at that moment. During strong geomagnetic storms, the energy input increases dramatically. The result is brighter, faster, and more complex auroras that can stretch across entire continents. Importantly, auroras are not dangerous to humans on the ground. They occur far above commercial aircraft and well above the breathable atmosphere. Earth's magnetic field and atmosphere together protect life from direct exposure to this energy. What we are witnessing is a controlled release, a safe discharge of cosmic energy into light. Auroras are nature's way of showing us how energy moves through space, interacts with magnetic fields, and transforms into something we can see. They are not random. They follow rules. They obey the laws of physics with astonishing precision. And yet, when we watch them dance across the sky, they still feel alive. That is the power of auroras. They remind us that the universe is active, dynamic, and constantly in motion, even when the night seems calm. Now that we understand how auroras are physically created, a new question emerges. Are all auroras the same? Or are there different kinds, formed by different processes? To answer that, we must explore the many types of auroras scientists have identified. Not all auroras are the same. Although they may all appear as glowing lights in the polar sky, auroras come in different forms, behave differently, and are driven by different physical processes. Scientists classify auroras based on how the particles arrive, how the light behaves, and where in the atmosphere the emissions occur. Let us begin with the most familiar type, the discrete aurora. Discrete auroras are the sharp, well-defined displays most people imagine when they think of auroras. These are the bright arcs, curtains, and rays that stretch across the sky and move with clear structure. They form when streams of energetic electrons are tightly guided along Earth's magnetic field lines. Because the particle flow is focused, the resulting light appears crisp and organized. Discrete auroras often respond quickly to changes in solar activity. During geomagnetic storms, they can brighten suddenly, split apart, or ripple with rapid motion. These auroras are typically associated with strong magnetic disturbances and substorms. They are the most dramatic and visually striking auroral displays. In contrast, there is the diffuse aurora. Diffuse auroras are faint, widespread glows that cover large areas of the sky. They lack sharp edges and often appear as a soft, uniform light rather than distinct shapes. These auroras are caused by lower-energy electrons that scatter as they enter the atmosphere. Instead of being tightly focused, the particles spread out, producing a gentle glow. Diffuse auroras are common during quiet geomagnetic conditions and can persist for hours. They are often present even when dramatic auroras are absent, but they may be difficult to see without dark skies. Next, we encounter a less familiar but scientifically important type, the proton aurora. Unlike typical auroras, which are caused by electrons, proton auroras are produced by protons, positively charged particles from the solar wind. When these protons enter Earth's magnetic field, they capture electrons from the atmosphere and become neutral hydrogen atoms. In this neutral state, they can travel deeper into the atmosphere before emitting light. Proton auroras are usually invisible to the naked eye. They are most often detected using ultraviolet cameras and satellite instruments. Although subtle, proton auroras provide valuable information about how solar particles interact with Earth's magnetic environment. Another fascinating category is the pulsating aurora. Pulsating auroras appear as patches of light that turn on and off rhythmically, sometimes several times per second. They are not caused by a steady stream of particles, but by waves in the magnetosphere that modulate the flow of electrons. These plasma waves act like gates, periodically allowing particles to enter the atmosphere and then shutting them off. Pulsating auroras often occur after substorms, during the recovery phase of geomagnetic activity. They can cover large regions of the sky and last for long periods. To the human eye, they feel almost alive, breathing, blinking, and fading in slow rhythms. Auroras can also be categorized by time of day. Most visible auroras occur at night because darkness allows us to see faint light. However, auroral activity does not stop when the sun rises. Daytime auroras exist, but they emit mostly ultraviolet and X-ray radiation. These wavelengths are absorbed by the atmosphere and invisible to our eyes, but they can be detected by satellites. Daytime auroras prove that auroral processes are continuous. The night sky simply reveals what is always happening. Another important distinction involves auroral substorms. During a substorm, energy stored in the magnetosphere is suddenly released. This causes rapid auroral brightening, expansion of the auroral oval, and intense motion. Auroras may surge toward the equator, split into multiple arcs, or explode into waves of light. Substorms are not random. They follow identifiable stages: growth, expansion, and recovery, and play a central role in auroral dynamics. Finally, there are rare and newly discovered phenomena that challenge traditional definitions. One of the most famous is Steve, a narrow purple arc that appears equatorward of the main auroral oval. Steve does not behave like typical auroras. It is not caused by electron precipitation in the usual sense, and its emissions come from extremely hot atmospheric flows rather than direct particle collisions. Its discovery reminds us that aurora science is still evolving. Even today, the sky can surprise us. Each type of aurora tells a different story about how energy moves through Earth's magnetic environment. Some auroras are sharp and explosive. Others are soft and steady. Some flash and pulse. Others glow silently for hours. Together, they form a complex language, a visual record of space weather written across the sky. And now that we understand the many forms auroras can take on Earth, a larger question emerges. Is Earth unique in this phenomenon? Or do other worlds also glow under the influence of their stars? To answer that, we must leave Earth behind and look outward into the solar system. If auroras are created by charged particles, magnetic fields, and atmospheres, shouldn't other planets have auroras too? The answer is yes. Auroras are not unique to Earth. They are a universal consequence of magnetism and plasma interacting with an atmosphere. Let us begin with the most dramatic auroras in our solar system. Those belong to Jupiter. Jupiter has the strongest magnetic field of any planet, more than 20,000 times stronger than Earth's. Its magnetosphere is so large that it would appear bigger than the Sun if we could see it. Jupiter's auroras are permanent, enormous, and incredibly powerful. Unlike Earth's auroras, which are driven mainly by the solar wind, Jupiter's auroras are largely powered by the planet itself. One of Jupiter's moons, Io, is extremely volcanic. It ejects vast amounts of sulfur and oxygen into space. This material becomes ionized and trapped in Jupiter's magnetic field, forming a rotating plasma torus around the planet. As Jupiter spins, once every 10 hours, its magnetic field drags this plasma around at tremendous speed. The resulting electrical currents funnel energy into Jupiter's polar regions, producing constant blazing auroras. These auroras emit intense ultraviolet and infrared radiation and can be hundreds of times more energetic than Earth's strongest displays. Next, we turn to Saturn. Saturn's auroras resemble Earth's in many ways, but operate on a larger scale. Saturn has a strong magnetic field and a thick atmosphere, allowing well-defined auroral ovals to form. Saturn's auroras respond to solar activity, expanding and contracting with changes in the solar wind, and they also display rapid motion and complex structures similar to Earth's substorm-driven auroras. However, Saturn's rapid rotation and ring system influence its auroral behavior in ways scientists are still studying. Moving farther outward, we encounter Uranus and Neptune, two planets with some of the strangest magnetic fields known. Their magnetic axes are tilted at extreme angles and offset from the centers of the planets. As a result, their auroras behave unpredictably. Auroral ovals on these planets shift dramatically as the planets rotate, creating unusual and asymmetric light patterns. Because these planets are so distant, their auroras are faint and difficult to observe, but space telescopes have confirmed their existence. Now let us consider Mars. Mars presents a special case. Unlike Earth, Mars does not have a global magnetic field. Long ago, its internal dynamo shut down, leaving behind only small patches of magnetic crust. For a long time, scientists believed Mars could not have auroras. They were wrong. Mars does have auroras, but they are localized. Instead of forming large ovals, Martian auroras appear in isolated regions where remnants of magnetic fields still exist. These auroras are faint and often invisible to the human eye, but spacecraft have detected them in ultraviolet light. Mars also experiences a different type of aurora when solar storms directly interact with its atmosphere, producing diffuse emissions across the planet. This shows us something important. A strong global magnetic field is not the only way to create auroras, but it shapes how they appear. What about Venus? Venus has a thick atmosphere, but almost no magnetic field. Any aurora-like emissions there are weak and rare, caused by direct interactions between the solar wind and the upper atmosphere. These emissions are difficult to detect and lack the structured beauty seen on magnetized planets. Beyond our solar system, aurora science enters a new frontier. Scientists have begun detecting radio emissions from distant planets that may indicate auroral activity. These signals allow researchers to infer the presence of magnetic fields around exoplanets, a key factor in assessing planetary habitability. Auroras, in this sense, become diagnostic tools. They help us understand a planet's magnetic strength, its interaction with its star, and its ability to protect an atmosphere. Auroras are not just beautiful, they are evidence. They tell us which worlds are magnetically alive. When we study auroras across the solar system, we see a spectrum of planetary personalities, each shaped by rotation, magnetism, atmosphere, and environment. Earth's auroras are balanced and graceful. Jupiter's are violent and permanent. Mars's are fragile and scattered. Each tells a different story. And now, having seen auroras as a planetary phenomenon, we must return once again to Earth, but this time to their impact on modern civilization. Because auroras are not just lights in the sky. They are signals of powerful space weather events that can affect technology, infrastructure, and life on Earth. Up to this point, auroras may seem distant, beautiful lights far above our heads, disconnected from daily life. But that impression would be misleading. Auroras are visible signs of space weather, and space weather has very real consequences for modern civilization. Space weather refers to the changing conditions in space caused primarily by the sun's activity. When the sun releases energy through solar flares and coronal mass ejections, that energy does not stop at producing auroras. It interacts with Earth's magnetosphere, atmosphere, and technological systems. Auroras are simply the part of that interaction we can see. When solar energy reaches Earth, it disturbs the magnetosphere. Scientists measure this disturbance using several indices, the most common being the KP index. The KP index ranges from 0 to 9 and describes the strength of geomagnetic activity. Low values indicate calm conditions. High values signal geomagnetic storms. As the KP index increases, auroras become brighter, more active, and visible at lower latitudes. But as auroras intensify, so do the risks. One of the most significant impacts of geomagnetic storms is on power grids. Rapid changes in Earth's magnetic field can induce electric currents in long conductive systems, such as power lines. These currents, known as geomagnetically induced currents, can overload transformers and cause widespread blackouts. In 1989, a geomagnetic storm triggered by solar activity caused the collapse of the Hydro-Quebec power grid, leaving millions without electricity for hours. Satellites are also vulnerable. Charged particles can damage satellite electronics, disrupt onboard sensors, and degrade solar panels. Increased atmospheric drag during geomagnetic storms can cause satellites in low Earth orbit to lose altitude. Communication systems are affected as well. Auroras indicate disturbances in the ionosphere, the same region that reflects radio waves. During intense auroral activity, radio communication can become unreliable or fail entirely. GPS systems may experience positioning errors, affecting aviation, shipping, and emergency services. Air travel itself is influenced by space weather. Polar flight routes pass through regions of increased radiation during solar storms. Our lines sometimes reroute flights to protect passengers and crew from elevated exposure and to maintain reliable communication. One of the most famous examples of extreme space weather occurred in 1859 during the Carrington event. A powerful solar storm caused auroras to appear near the equator. Telegraph systems sparked, operators were shocked, and some messages were transmitted even after power supplies were disconnected. If an event of similar magnitude occurred today, it could cause trillions of dollars in damage. This is why scientists closely monitor solar activity. Modern space weather forecasting scientists closely monitor solar activity. Modern space weather forecasting uses satellites positioned between Earth and the Sun to provide early warnings of incoming solar storms. These warnings allow power companies, satellite operators, and airlines to take protective measures. Auroras, therefore, are not just beautiful phenomena. They are alerts. They tell us when Earth's magnetic shield is under stress. They remind us that our planet exists within an active solar environment, one capable of influencing every layer of our technological world. Yet, despite these risks, auroras also demonstrate the effectiveness of Earth's magnetic field. Without it, solar storms would directly strip our atmosphere and bombard the surface with radiation. Auroras are the visible proof that Earth is absorbing, redirecting, and safely releasing vast amounts of energy. They show us a planet actively defending itself. And as we move forward, our ability to predict auroras improves, not just for beauty, but for survival. But to predict them accurately, scientists must understand them in detail. That brings us to the tools, instruments, and missions used to study auroras. How do we measure something that happens across hundreds of kilometers of sky? How do we observe particles we cannot see? Auroras are vast. They stretch across continents. They occur high above the surface of the Earth. And yet scientists study them with remarkable precision. Understanding auroras requires observing something that cannot be touched, cannot be captured, and often cannot even be seen directly. To do this, scientists rely on a combination of ground-based instruments, space missions, and theoretical models. Let us begin on the ground. Across polar regions, researchers deploy all-sky cameras. These cameras use wide-angle lenses to capture the entire sky at once. By recording time-lapse images, scientists can track auroral motion, shape, and intensity over time. These images reveal patterns that help identify different types of auroras and their relationship to geomagnetic activity. Another crucial ground-based tool is the spectrometer. Spectrometers analyze the light emitted by auroras and break it into its component wavelengths. This allows scientists to identify which atoms and molecules are emitting light and at what altitudes the emissions occur. Through spectroscopy, researchers confirmed that oxygen and nitrogen are responsible for auroral colors. Ground-based radar systems also play a major role. Facilities such as IceCat transmit radio waves into the ionosphere and measure how those waves scatter back. This provides data on particle density, temperature, and motion within the auroral region. Radar allows scientists to observe auroras even during daylight or cloudy conditions. But ground-based observations only tell part of the story. To truly understand auroras, scientists must go into space. Satellites orbiting Earth carry instruments that directly measure charged particles, electric fields, and magnetic fields. Missions such as Themis, Cluster, and Swarm were specifically designed to study the Sun-Earth connection and the processes that drive auroras. These spacecraft fly through the magnetosphere and auroral regions, sampling particles as they move toward Earth. Some satellites operate in coordinated formations, allowing scientists to observe auroral processes in 3 dimensions and track how energy flows through space. Another powerful research tool is the sounding rocket. Sounding rockets are launched from polar regions and travel briefly into the upper atmosphere before returning to Earth. During their short flights, they carry instruments directly through auroral arcs. These rockets provide high-resolution data that satellites often cannot, capturing fine-scale structures within auroras. Because auroras change rapidly, these short missions are invaluable. High-altitude balloons have also been used to study auroral effects, particularly atmospheric changes and particle interactions. In recent years, auroral science has benefited from unexpected contributors. Citizen scientists, photographers, and observers worldwide now provide valuable data. Their images help track rare auroral forms and confirm satellite observations. One of the most notable examples is the discovery of Steve, which was first reported by amateur observers before being studied scientifically. Modern auroral research also relies heavily on computer simulations. Scientists use plasma physics models to simulate how particles move through magnetic fields and interact with Earth's atmosphere. These models help explain observations and test new theories. Artificial intelligence and machine learning are now being used to predict auroral activity by analyzing vast amounts of space weather data. Together, these tools form a complete system. Ground instruments observe the sky. Satellites measure the space environment. Rockets probe the auroral zone. Models tie everything together. Auroras are no longer just seen, they are measured, mapped, and predicted. And yet, despite all this technology, auroras still hold mysteries. Some structures appear smaller than any current model predicts. Some behaviors change too rapidly to be fully understood. This reminds us that aurora science is still evolving. And that leads us naturally to the frontier, the unanswered questions. What don't we fully understand yet? What puzzles still remain in the glowing sky? After centuries of observation, decades of space missions, and enormous advances in physics, it might seem that auroras are fully understood. But that is not the case. Auroras are among the most studied natural phenomena in space science, and yet they still hold unanswered questions. At the heart of aurora research lies a fundamental mystery. How exactly are particles accelerated to the energies required to create auroras? Scientists know that electrons are guided along magnetic field lines toward Earth. They also know that electric fields and plasma waves play a role. But the precise balance between these mechanisms is still being studied. In some cases, strong electric fields appear to pull electrons downward like a voltage drop in a circuit. In other cases, interactions with plasma waves scatter particles into the atmosphere. Which process dominates and when remains an active area of research. Another mystery lies in the fine-scale structure of auroras. High-speed cameras reveal auroral features only a few meters wide that change in milliseconds. These structures are far smaller and faster than many models predict. Understanding how such small-scale patterns form in a vast magnetospheric system is one of the biggest challenges in aurora physics. Then there are pulsating auroras. Scientists know they are linked to wave-particle interactions in the magnetosphere, but why they pulse with certain rhythms and why they persist for hours after geomagnetic storms is still not fully explained. Some auroras also appear to drift or flicker in ways that defy simple magnetic explanations. And then there are discoveries that rewrite the rules. The appearance of Steve, a narrow purple arc unrelated to typical auroral mechanisms, forced scientists to reconsider what qualifies as an aurora. Steve is associated with extreme ionospheric heating and fast atmospheric flows, not direct particle precipitation. Its discovery shows that Earth's upper atmosphere can glow in unexpected ways. Another open question involves auroral sounds. Some observers report hearing faint crackling or popping noises during intense auroras. Although controversial, recent studies suggest that under certain conditions, electromagnetic disturbances near the ground could produce audible effects. The debate is ongoing. Auroras also raise questions about energy transfer efficiency. Only a fraction of the sun's energy reaching Earth is converted into auroral light. Where does the rest go? How is it distributed through the magnetosphere and atmosphere? These questions matter beyond Earth. Understanding auroras helps scientists model how stars interact with planets across the universe. It informs research into space weather, atmospheric loss, and planetary habitability. Modern auroral research is increasingly interdisciplinary. It combines plasma physics, atmospheric chemistry, magnetohydrodynamics, and even data science. Artificial intelligence is now being used to detect patterns humans might miss and to predict auroral activity more accurately. Yet with every answer, new questions emerge. Auroras remind us that nature operates across scales, from atomic collisions to planetary magnetic fields to stellar explosions. They are a reminder that even familiar beauty can hide deep complexity. And as we approach the conclusion, what do auroras ultimately teach us? Not just about physics, but about our place in the universe. To answer that, we move to the final chapter. For most of human history, auroras were not understood. They were feared, worshipped, and woven into myths. They were interpreted as messages from gods, spirits, or the sky itself. And in a way, those interpretations were not entirely wrong. Auroras are messages, not supernatural ones, but physical ones. They tell us that Earth is not isolated. They tell us that our planet lives inside the influence of a star. They tell us that invisible forces are constantly shaping our environment. Auroras reveal something fundamental about Earth. They show us that our planet is protected. Earth's magnetic field shields us from the sun's constant flow of charged particles. Without it, our atmosphere would slowly erode, and life as we know it would struggle to exist. Every aurora is proof that this shield is working. When energy from the sun arrives, Earth does not absorb it blindly. It redirects it, it controls it, and in doing so, it releases part of that energy safely as light. Auroras are the visible signature of planetary survival. They also remind us of fragility. Our modern world depends on electricity, satellites, communication networks, and navigation systems. All of these are vulnerable to space weather. Auroras are beautiful, but they also signal moments when Earth's magnetic environment is under stress. In that sense, they are warnings as well as wonders. Auroras also offer perspective. They show us that beauty does not always come from calmness. Sometimes beauty emerges from conflict, from collisions, from energy transfer, from motion. The dancing lights in the sky exist because particles collide at tremendous speeds. Order emerges from chaos. And perhaps that is why auroras affect us so deeply. When we stand beneath an auroral sky, we are not just observing physics, we are witnessing our planet interacting with the cosmos in real time. We are seeing a process that is happening above us, around us, and beyond us, whether we notice it or not. Auroras make the invisible visible. They turn magnetic fields into motion. They turn solar storms into color. They turn space into something we can see and feel. As science advances, auroras continue to guide us. They help us understand space weather. They help us protect technology. They help us search for magnetic worlds beyond our solar system. And they remind us of something essential. We are not separate from the universe. We are part of a dynamic system, one where stars, planets, fields, and particles are constantly interacting. When the sky glows with auroral light, it is not putting on a show for us. It is simply being honest. It is revealing the hidden forces that have always been there. And when we look up and feel awe, that feeling is not ignorance, it is recognition. Recognition that we live on a living planet beneath an active sky, orbiting a powerful star. That is what auroras truly are. Not just lights in the night, but a reminder that the universe is alive and we are inside it. If this journey helped you see the aurora differently, If it made the night sky feel a little more alive, please take a moment to like this video. It helps this story reach others who are still looking up with questions. If you want more deep, calm explorations like this, stories that slow the world down and explain the universe around us, subscribe to the channel. And if someone you know has ever stood under the northern lights or dreamed of seeing them one day, share this with them. Have you ever seen an aurora in real life? If yes, where were you and when did it happen? And if not,